I wouldn't say as 15 or something that I would say, yes, what I'm doing now is what I think I would do. The entrepreneurial stuff, again, really only came during my period at MIT. I think I saw myself as an academic, and I think traditionally this sort of bridge between academia and industry, or even spin-outs, was frowned upon. It's sort of not something that's natural. I think MIT, is a very good exception. I think Cambridge is a very good exception, where it's very much that there are many academics who are very successful at doing it. But by and large, the academic world and the physics world, it's uncommon to have, a startup or entrepreneurial sort of activity. So I never thought of myself I would be an entrepreneur until I started learning about the entrepreneurial world and realizing I enjoyed it.
Welcome to People Doing Physics, the podcast that explores the personal side of physics of the Cavendish Laboratory at the University of Cambridge.
Hello, I'm Jacob Butler from the Outreach Office.
And I'm Vanessa Bismuth, the Cavendish Communications Manager.
Today we're joined by Professor Sam Stranks, Professor of Optoelectronics and Royal Society University Research Fellow in the Department of Chemical Engineering and Biotechnology, and a Cavendish Joint Member here at the Cavendish Laboratory. Growing up in Australia, Sam graduated from the University of Adelaide with a BA in German and Applied Mathematics alongside a BSc in Physics and Physical Chemistry before completing a PhD at Oxford University. His research focuses on developing novel materials for low-cost electronics applications, such as solar cells and LEDs, and he is co-founder of Swift Solar, a company taking this technology to market by developing lightweight perovskite solar panels. If working in business and academia wasn't enough, Sam teaches at the university, setting up several new PhD programs, and is one of the co-founders of Sustain Ed, a national charity developing content for primary schools looking at climate change solutions. In this episode, we'll talk about his multidisciplinary route through science, how he manages to keep a foot in both research and industry, and just how many times he came close to dropping physics entirely. Stay with us. So first of all, welcome Sam, thanks for joining us.
Thanks for having me on.
It's quite all right, and as I've all started at the beginning, so when did you first start getting interested in sort of science and scientific thinking?
Yeah, so I think I look back at even in primary school, I think I was quite interested in how the world works, and I think particularly learning about the mechanics of things, and I think sort of intuitively I had a lean towards physics even at that point, even though I hadn't started any physics. And it wasn't until high school where I really started picking up physics and maths and seeing how they interconnect, and seeing that we can explain a lot about the world through physics.
And you mentioned in an earlier chat that your grandfather was a scientist as well. I mean, was this something that sort of helped spark your interest?
Yeah, absolutely. So my grandfather, Don Stranks, he was a chemist, a professor in chemistry. Actually, he was in the UK for a few years, and then he was a professor in Melbourne in Australia, and then actually he was Vice Chancellor of Adelaide University. Unfortunately, he passed away when I was only 2, so I never met him, but his science certainly has inspired me. In fact, he worked in somewhat similar area, actually, particularly looking at electron transfer chemistry. So I cited him in my PhD thesis, which I was very excited about.
You want to talk to us about your teachers as well? Understand that your teachers made a great impression on you.
Yeah, I think so. Particularly in high school, I think I had 2 very good physics high school teachers who were really inspiring. They were very rigorous, somewhat strict, but certainly rigorous, and really, I think instilled the excitement physics can bring. And particularly how it can explain the world, and particularly also how it connects with maths as well, which is something I'm also quite passionate about. I like that connection.
So is that how you made that choice to go to university? Because you studied German in university, as well as science. So do you want to talk to us about your choices there?
Yeah. So I think the way to describe it is I did quite a broad undergraduate degree. I'm quite interested in several things. First and foremost, it was the sciences, physics, chemistry, and maths that I really enjoyed at school that I wanted to keep carrying on. But I also enjoyed travel a lot, and actually after I finished high school, travelled through Europe and enjoyed being in Germany. So I decided I wanted to learn German. I actually have a grandmother who's German as well, who's Austrian, sorry, but and I wanted to be able to speak German with her, so that inspired me to do that. I really quite like that at least the undergraduate degree I did in Adelaide in Australia did allow me to do these 2 very disparate and separate degrees concurrently, a Bachelor of Science and a Bachelor of Arts, but I found that really, really useful for having a broad understanding of how things work and and even the language side of things.
So in the natural sciences side of things, did you pick up physics quite early on, or did you explore different disciplines?
So I started my first year doing physics, maths, chemistry, because I liked that from school. I had a plan to actually do medicine from there, and I started picking up biology. In fact, I did biology my first year as well, which is a new world to me, but I quite enjoyed it, and then had a track towards doing medicine. I dropped physics and maths entirely just to be able to sort of fit in a track towards a more medical science-based degree, and actually was 2 weeks into that in my second year and realised that I missed physics and wanted to go back to it, so I flipped back and ended up carrying on in a Bachelor of Science with physics as one of the majors. And then actually at a second point, after finishing undergraduate, I had a place in medical school, in graduate medical school in Australia, that was my path was going to be medicine. My parents and family are all mostly in the medical area, so I sort of saw that as a somewhat natural path. But again, couldn't shake that I really liked the physics, and I didn't want to give that up. And fortuitously at the same time, I also got the Rhodes Scholarship to go to Oxford, which then enabled me to go and do a PhD in physics. And that's a bit of a very big sliding doors moment for me, which I look back on, but certainly have no regrets.
Mm. We'll go back to that later on in the conversation, but I think you managed to find ways to bring medical field into your own work.
So what was it that you looked at during your PhD in Oxford?
Yeah, so I generally was working on emerging semiconductors for solar photovoltaics, and it was in fact my first step into the world of materials for solar cells. I was specifically working on organic materials, so actually carbon nanotubes and wrapping carbon nanotubes in polymers. The polymers absorb light really well, and the idea is that polymer absorbs the sunlight and energizes electrons, and those electrons inject into the carbon nanotube, which then zooms to an electrode and could be collected. So quite an interesting mix of chemistry, some wet chemistry and processing these materials, but also in the physics of understanding that electron transfer and those energized electrons. So it was quite a nice mix, and I think it's been quite a theme for my career since. Those materials, of course, were relatively early stage, and I think we certainly found some good science. I think from a practical aspect, they're still quite hard to make efficient. These carbon nanotubes are particularly hard to synthesize in a very pure way. So I think there's some fundamental limitations that might stop them from becoming a really mainstream solar material. But I certainly learned a lot and really springboarded me to the next point in my career.
Oh yeah. And it sounds like it sort of crossed over into renewables a bit then. Was this a sort of conscious choice that you made, or was this just something you found yourself sliding into?
Yeah, no, it's a conscious choice. It's something I've certainly seen, actually even through high school, seeing climate change as one of the biggest challenges society faces and continues to be. So I was very inspired to use the science and the physics and chemistry that I've been learning to be able to apply it to an area that I'm passionate about. So when I was looking, I had the scholarship to go to Oxford, and I was looking at potential PhD projects. I really was particularly looking in renewable areas that attracted me, and that happened to do so. And I was worked with Professor Robert Nicholas and Michael Johnston in the Clarendon in Oxford.
Oh, that's excellent. I mean, yeah, a lot of the kids we get in seem to like physics, but struggle to see how it applies to things and how this sort of very fundamental sounding research can tie into actual technologies and things like that. But you then went on to a postdoc in which you first used perovskites. Now, are these something you're still looking at, or is this sort of historic technology?
Yeah, so still a core part of the group. We're looking at these halide perovskite materials. So this is in 2012 when I finished my PhD. My wife and I wanted to stay in Oxford for a bit longer. She was finishing her PhD and doing a postdoc. So I joined Henry Snaith's group in Oxford in 2012, and actually that fortuitously was the time when the first perovskite solar cells were coming along in that group. So it was a very exciting time to join. I actually joined to study dye-sensitized solar cells, and very quickly started on these new materials, and that was an extremely exciting time. It was, every day, every week, a new discovery around this material, because they hadn't really been studied before. They're a material that they're emerging semiconductor. They're essentially an ionic material that's essentially a human-made mineral that we can solution process in the lab very inexpensively, but they perform really well. And actually that was the really surprising thing, that from that early stage, they were already performing very well as a semiconductor, and bringing surprises in terms of the photophysics that we were understanding, and that meant it was a very exciting postdoc period, 2 years there, and that again springboarded me to the next stage of my career as well.
So yeah, talking about your next stage, what was your next stage? You went on to the US.
Yeah, so I went to MIT then. I was fortunate enough to get a Marie Curie fellowship, which took me out from the UK to the US for 2 years. I worked in an electrical engineering department there with Vladimir Bulovich, and continued working on perovskite solar cells and developing the materials themselves. Some of the things I started picking up there was around trying to understand the nanoscale and the microscale properties of these materials, so really zooming in with microscopes to understand the photophysics on very small length scales. It actually turns out that those length scales really matter for these solar cells, even though we think about a big module that's meters squared. Actually, it's really the nanoscale that really matters a lot. We're seeing a lot of the performance losses and the instabilities in the material actually start arising from that very small length scales. And so that during that period, that postdoc period, that's when I started understanding that and developing these ideas around these small length scales. I think the other thing that was really exciting about MIT was the entrepreneurial vibe. It's a really exciting place for that. And in fact, that was really where the first conversation started that led to Swift Solar, the founding of Swift Solar, with a colleague there who's now the CEO, Joel Jean, working together with him closely in the lab. He was a PhD student at the time. We had some really exciting ideas together with some colleagues at Stanford as well, who were also co-founders, and also some of us, in fact, reach back and date back to our Oxford days together. Several of us moved across to the US to work there.
What was so particular at MIT that you found so inspiring in terms of like entrepreneurship, and what was it about that made you?
I think it's hard to put a finger on. It's part of the fabric of the institute. I think that, almost all students, each student who comes into the lab, whether they're an undergraduate student or a graduate PhD student or a postdoc, there's sort of some excitement about how that technology could be used and or commercialized or licensed out. And in fact, there's almost many of the students I interacted with, there is a sort of a mindset that that's a pathway they want to follow. They want to take, have an idea in the lab that they can then take and spin out. And I think there's MIT facilitates that really well. There's a very good system in place there. I actually think Cambridge does a very good job of that too, but MIT I think is very much the model for how one can take really quite fundamental lab-based research and spin it out and be very successful doing that.
So you mentioned Swift Solar. Do you want to tell us a bit more about what this company does?
Yeah. So Swift Solar is a US-based company based in California. The aim is to produce very high efficiency solar modules using these halo perovskite materials. So it's something where we can layer two perovskites together or layer perovskite and silicon together. So silicon is the current mainstream technology for photovoltaics. We can add a perovskite layer on top and actually, which is a tandem technology, and move well beyond the efficiency of silicon. And in the longer term, doing that with replacing silicon and doing that with two perovskite layers. And so these two layers absorb slightly different regions of the solar spectrum, slightly different colors. So working together, they can get around the traditional efficiency limits that one layer alone would have. And so we're commercializing this technology, particularly towards the high efficiency solar, and particularly thinking about how scalable ways to manufacture these materials and how to make them extremely stable for decades.
So I imagine that's quite a different sort of mindset to the one you'd have in the lab when you're working at those nanoscales and with very sort of fundamental technologies. Is that something you actively sort out? Or?
Yes, it is, and I think it's something I really like, having that connection with the big picture and the scale up and those very different scientific and engineering questions than we maybe focus on in the lab, but they actually do connect quite strongly because I mentioned before about how the nanoscale and the microscale really do matter. We're seeing these heterogeneities on small length scales that might not seem significant, but actually do end up mattering for the large scale modules. So for example, we see very small impurity phases that can appear in the manufacturing process that end up being sites that degrade the cell and start degrading the performance. So we need to understand them, and that's really what we're doing in the lab, understanding why they're there, how they're there, and then thinking about solutions to remove those unwanted phase impurities. And that ultimately will help the long-term scale up and also the performance.
Yeah, and you talked about them sort of degrading over time and things like that. I mean, obviously this is technology that can be sat in a field for years, if not decades. I mean, you talked about simulating wear in our previous conversation. Is that sort of, can you explain a bit about that and why that's useful for this?
Yeah. So a big challenge is, so currently if you buy a silicon module, it will last for 25 years. It'll be guaranteed for 25 years. It'll probably last for 40 years, some of the best panels. So there's a bar that's set very high for a new technology that needs to come through. One of the big challenges there's two challenges with that for the perovskites. One is it's a new technology, so to be able to validate it to last for decades, you need to think about ways to test it in an accelerated fashion, that we can get feedback much faster than decades. Even over months of testing, we can understand what that would be equivalent to in terms of years in the field. So we and others in the field are coming up with methods for testing cells at elevated temperature, for example, with continuous operation with different bias conditions to really try and mimic the field operation conditions, particularly to get feedback on, again, some of these impurities, these performance losses, and how that could feed back to the manufacturing process. And the second is that it's an emerging material. It's not yet stable enough to say it will last, that we can say with confidence that it will last for 25 to 40 years. That's a materials challenge that still needs to be solved. There's been very good progress in the last few years to make the material a lot more stable. The first configurations, that we were working with in 2012 type region, they were quite unstable, but over the decade effectively since, there's been a lot of work on the compositions, a lot of work on the deposition process to make them a lot more stable. And now, even over the last year, some of the results that are coming out, both from academia but also from industry, are looking extremely exciting. And I think I would put probably now it's been validated at least at 5 years, and it's mainly a function of it hasn't been tested for long enough to guarantee longer than that. So there's still some way to go to get to the 25 years, but it's a very exciting trajectory.
That's good. So it's at least 5 years for now. And
at least validated for 5 years. I would say it will last for longer, but we're not yet able to guarantee 25 years.
So how is it back and forth between your work in the lab as like research fundamental level and in your company, and between the lab and the industry? How does that work? So one feed the other, but does the other feed back? Yeah,
no, very good question. I think the role is quite separate. There is, we're focusing on the fundamental work in the lab. In the company, I'm a co-founder, and early on was obviously very heavily involved. I'm now a scientific advisor in the company, and really more giving the academic perspective on what we and others in the academic world are learning and how that can feed to the industry. We do actually, it is both ways, because I think particularly what's important is understanding from industry what the questions are we need to tackle, because I think it's, we as academics are sometimes at fault of projecting what we think is the problem onto industry, but actually when you speak to them, they have a very specific set of questions they want answered, and that's where there's very fruitful collaboration as well. And that's not just this example, that applies in many other areas of industry academia interaction, where that is fruitful, where we can really understand the questions and then tailor some of the academic approaches and questions towards those problems.
Does it help focuses your research, because it's almost like looking for a needle in a haystack sometimes? Yeah,
it is. I think it does focus it in that sense, but I think it's important also that's not the only work we work on. It's the real value of academia is that we have freedom to and new ideas that can be disruptive, that come along that we haven't thought of before, others haven't thought of before, and I think it's important to have that the mechanisms there such that a lab can produce these new things that could eventually feed onto existing or new industry, including through new startups. So I think that's again also why I find my academic role really exciting, is that there is those new elements. It's not just solving some of the problems that industry want, but also thinking about how we can generate the new technology that could surpass what is currently out there.
Actually, do you want to tell us a little bit about the other big questions that you're trying to answer in your lab, in your research work?
Yeah, we have a big stream is on photovoltaic research, but we're also looking at lighting technologies as well. So we're looking at, in fact, if you run a solar cell in reverse, so a solar cell is harvesting sunlight and generating electricity. If you run it the other way around, where you inject electricity in, you get light out. So that's an LED So effectively, the same materials that we've been using for solar cells are actually very good LED materials as well. And so a big strand of our lab is thinking about how to produce efficient blue, red and green emitters, for example, that could be used for displays or for white panel lighting as well, to make more efficient and better color quality white lighting. And then another area that we're working on actually is in actual medical imaging, and applying some of these semiconductors where, again, we're developing for PV, but for X-ray detection. So here, for X-ray detection in medical images, for example, what we need is, in a solar cell, we only need 500 nanometers of material to absorb those optical visible photons. For an X-ray, we need millimeters of material. So it's essentially we're moving towards very thick solar cells that harvest the X-rays and then generate electrons and holes that we can collect. So it operates like a solar cell, but for a very different application. And so we're developing these halide perovskite materials towards X-ray detector applications, and really the application is moving towards very, very sensitive X-ray detection. So if you have a patient, for example, having a CT scan, the X-ray passes through the patient, that detector on the other end we can make extremely sensitive. And so that means that the dose of that X-ray that has to pass through the patient can come down significantly. And one of the limitations at the moment of X-ray scanning or CT scanning, for example, is dose, so that radiologists would need to consider, and the patient would need to consider, if it's the right thing to have a scan or not. We want to flip that around and have it so that it's so low dose that you can even use it for screening. So you can think about very early stage disease detection for cancer, for heart disease, and monitoring over time. And that's something very exciting, we know, to radiologists as well, how they could, for example, see the change in something over time. If there's a small tumor, very early stage of that, they could see how that's evolving over time, and then they can make decisions on how to treat that in a much more guided fashion. So we're very excited about this. We actually have a very recent startup spinning out from the lab here in Cambridge, Clarity Sensors, to commercialize this technology. It's very early stage, but we have a very exciting trajectory here, leveraging these very efficient halide perovskite materials towards medical imaging detectors.
And a very subtle way of bringing back the medical field into your work, and to please your family as well. And to be able to explain that I work in medical sciences as well. Well done. Yes,
it's something very exciting to me. I think it's another, healthcare is another very big problem, and if we can use, again, the physics and the semiconductors we can produce to make an impact there, it's a fantastic opportunity.
Yeah.
I do think it's great about physics that you find this technology, and it's it's useful for generating electricity, generating light, and also slightly different format. You can use it in a very different sort of environment for doing very different sort of things. So from the outside, sort of industry and academia look very different, but you're someone who sort of crosses both those boundaries. Do you find it sort of a difficult process moving from one to the other, or what's
I think feel like certainly early on, it was a very steep learning curve, learning the business world, and particularly being involved at a very early stage in a startup. You learn a lot of things very quickly, and others who've done startups, I'm sure, will have the exact same experience, that they've had to be doing all these multiple tasks at once while learning how to do these multiple tasks. So there's a challenge in that, but that has been very rewarding. I've certainly learned a lot about the business world and how these technologies could fit into that, how the things we do in the lab could end up making an impact. In terms of sort of interacting between the two, I think it's also it's certainly helped with interactions with other industry partners and how we work with them to understand sort of the working mechanisms of a business, of a technology business, and how that moves along, and that's certainly enriched my career a lot. I really like that bridge between the fundamental work we do in the lab, the teaching that we do, but then how that could then be applied to the industry world.
So you talked about sort of needing that change in perspective at times in our earlier chat. I mean, how do you view the different perspectives of business and sort of research?
Yeah, I think, both extremely important, and I think it's working out where, even me as an individual, where I can sort of get the most, add the most value as someone who can work as an academic, but also have a hat on as as someone in industry, who works with industry or in industry, and I think that's making sure finding that balance is tricky, and I think it comes back to the fact really the academic world can produce the new ideas and and the new innovative things that industry just don't have the bandwidth for, or just don't have the resource for, that industry could then adopt. And I think that's again something I find very exciting.
So looking back at a younger version of you, did you ever think that you would did you have a clear picture of what your career would look like? Did you picture you as an entrepreneur or an academic, or at this hybrid model?
It's a very good question. I think when I look back long enough ago, I saw myself as an Australian footballer, professional Australian footballer.
Speaking
so a very
German.
different world. Yes, but and actually I played a lot of Australian football to sort of semi-pro level in Australia. But
which one is the Australian football? Is that soccer or is it?
No, it's a completely different game.
Okay.
Yeah. It's a mix between rugby and soccer. Probably is the best way to
right,
put
that
it.
One.
Somewhat similar to Gaelic football, if you know the Irish game. But so that anyway. That was a very different path than when I was. If you ask my probably 12-year-old self, that would have been my answer. But I think I did. When I was when I was at school and even an undergraduate, I didn't really know what an academic does really, and maybe that's something that's sort of a common theme. It's the way you interact with academics as an undergraduate is you see them as lecturer, but you don't actually know. Most of their time is actually spent. A lot of their time is spent on research, and that's a whole different world. They're not resting over taking a break over the summer. It is getting back to the other work, and I think I always enjoyed, the disciplines I studied, and it was a natural path for me to then just keep going and towards an academic career. I didn't know much about research either. Even as an undergraduate, until doing a final year honours master's project where you really get to dive into research. So that was something, an uncertainty of if I want to be an academic, research has to obviously be something I like doing, and it happened to be I really liked it. In fact, liked it even more than the theory and the coursework I was doing. So, but I think I wouldn't say as 15 or something that I would say yes, what I'm doing now is what I think I would do. The entrepreneurial stuff again really only came during my period at MIT. I think I saw myself as an academic, and I think traditionally this sort of bridge between academia and industry, or even spin-outs, was frowned upon. It's sort of not something that's natural. I think MIT, is a very good exception. I think Cambridge is a very good exception, where it's very much that it is. There are many academics who are very successful at doing it, but by and large, the academic world and the physics world, it's uncommon to have, a startup or entrepreneurial sort of activity. So I never thought of myself I would be an entrepreneur until I started learning about the entrepreneurial world and realizing I enjoyed it.
That really is a matter of grasping the opportunities when they come.
Yeah, exactly. Yeah.
So you talked about teaching already quite a lot, but let's go back to it because it's an important part of your activities as well. And you're setting up PhD programs, and you founded this charity with your colleagues. Do you want to tell to us about SustainAid first?
Yeah, sure. Yeah, so Sustain Education, it's a charity that we founded, so me together with two of my former postdoc and a former PhD student, so Stuart McPherson and Beth Tennyson, who are both here in the Cavendish. And I suppose the challenge we wanted to solve is that at the moment, climate and the fact there is an impending climate crisis, primary school kids know that this is a problem. They're taught that there is a growing problem, but they're not taught that there are solutions. So actually there's a growing issue that many 10, 11-year-olds are getting this climate anxiety that's coming in because they know there's a big problem, and it's probably them who will be facing that problem, because unfortunately they'll be the ones at the peak of their career when 2050 comes. So what we wanted to do, the aim of SustainAid, is to develop teaching materials that teach not just the problem, but also that there are solutions and technical solutions coming along that can feed into this. There are renewable energy technologies coming along, teaching them about what they are and what the future of those look like, and how they play a role in decarbonising society. And so we've developed a whole lot of teaching modules with packages that we have open sourced and make available to teachers. We piloted it in a few schools across Cambridge here over the last 4 years, and now we're in 40 schools across the country, and in fact around 1,200 teachers who've downloaded the materials now from our website. and teachers are then free to adapt them how they like to fit their own curricula. And so this has been really exciting. It's something, again, a slightly different world again, with education at a much earlier level. We of course had lots of good input from teachers along the way to develop those materials, and it's something we want to scale further as well, because it's something we see could be in every school across the country, or even broader than that, because they are materials that can be sent out remotely, and teachers can then pick up and adapt them as they like and fit into the Year 5 and Year 6 curricula.
And beyond reassuring those youngsters that solutions are possible and there's a way to try and fix or solve the issues, are you also hoping to inspire future physicists and future scientists?
Yeah,
in
absolutely.
general?
Yeah, that's another aim of it. I mean, we sort of embedded within the curricula is sort of generating the excitement about the physics that underpins a lot of these technology innovations. And so we do, for example, as part of the module we supply for the teachers, they have a little device they can measure the wind. The students can measure the wind, and they can also measure the solar intensity. So every day in the schoolyard they would go out and take a reading of the wind and the solar, the sunlight, and then they'll log it in their logbook, and actually it goes on the website. And so those students get opportunity to work with numbers and how to convert numbers. They in fact do some calculations of how much energy that would be in total across the course of a week or across the course of the year. So they get to know so some of the maths that is needed. But really there is a good opportunity to inspire what will be the next class of physicists and scientists and engineers who'll be the ones really tackling these problems towards 2050.
I think it's great to show these kids that there's lots of ways they can help as well, because if the kids we get through for the outreach things, quite often the ones that want to help see medicine as the only way they can do that.
Yep.
Whereas actually in the real world there's huge numbers of careers with huge numbers of different things, and it's great to show these things at an early age.
On a side note, I just remembered, I think we interviewed Stuart Macpherson, who is one of the founders in this podcast. So we'll put the link. We'll put the link in the show notes as well for anyone who wants to listen back. And in terms of the PhD programs here at Cambridge, do you want to tell us about the new one that you're setting up?
Yeah, exactly. So we've just set up a new PhD program. It's just been approved actually a few weeks ago. So it's a PhD in Sustainable Energy Materials Innovation. It's going to be a PhD program that is, it's in fact based here in the Cavendish, but it spans across 5 different departments across the university. And the aim there is for students to come in to do research on new energy materials technologies towards the net zero industry. And I think one of the really unique parts about the course is that students will be in a cohort where they're together with colleagues who are all working on different energy technologies. So I have fellow students, there might be one focusing on battery technologies, another focusing on solar technologies, another perhaps on low energy computing technologies, and they'll be able to interact and use expertise across those different fields and interconnect those expertise, which is something we've found really good spot examples of that already happening across West Cambridge. We wanted to formalise that in a course where students can really benefit from that. And so the students coming out will have not just their own research in their particular area, but broad awareness across the energy technology landscape, where their own energy technology fits into the wider energy landscape, and how it fits in, for example, how policy plays a role in that, how finances plays a role with that, how behavioural change plays a role in that. So it's something we see as very exciting. So this is together with Sian Dutton, we're co-directors of the course. We'll be taking our first PhD students in the 2025 intake, October 2025, so we'll be in the next few months advertising out for admissions for the course.
Excellent. We'll put also the links in the show notes.
Sounds excellent course, and from a lot of our sort of interviewees we've heard about the important exciting things happen at those fuzzy edges between disciplines, and it sounds like a course really built around encouraging that sort of cross-pollination and wider understanding at least of what the context in which you're working in.
Exactly, yeah. So that's, I think, even from my own career, and I know many other colleagues are the same, we find that the interactions with the other disciplines is where some really good innovation happens. And in fact, in many ways, it's, I'm in chemical engineering biotechnology department is my core appointment, but I'm a physicist, and we have many examples of that across Cambridge, where there's academics working in many different fields and departments, and I think that's really adds to the richness of this place, that we have people who work at the discipline edges and interact really well. And that's, I think, something that we, it's exciting for our own research, but also for the students and the postdoc and the staff who come along and interact with us and the programs.
That's also the principle of the natural sciences tripos, like for undergraduate students, right? To have that overview of all the disciplines.
Exactly. Yeah, it's core to Cambridge, and I think it's really important we do that. That students can come in and have a broad, broad, particularly their first years in natural sciences, because many students, like myself, may do subjects that we had never done at school, never knew existed, and end up being a big part of what we actually end up doing in our careers. So I think that's really important. I think in many places in the UK, people come in directly to a physics degree, for example, but don't get that broad understanding. So I think we're quite fortunate here to have this system. I'm very happy.
So it's only logical that it continues throughout the PhD program as well. Yeah, absolutely.
Lovely. I think I'm going to bottle that answer for next time I help out the open days and I get the students asking me, why can't I just do physics?
Yeah. Yeah. And I think again, something that excites me a lot is that physics does underpin a lot of these, a lot of what we see in the world, a lot of technologies, and that's again why I find, as a physicist, I really like working in these areas that are applied, that I can use the physics to apply them in these different areas.
Lovely. And any other plans for the future that you wanted to bring up that we've not gone through, or anything else you wanted to add to finish us off?
No, I think that covers everything. I hope we can make meaningful impact on climate change and on these big global challenges, and that's through both the technology, but also through the students and postdocs and staff that we train through the system. That this collective effort will make the impact in the long term, and that's something that excites me a lot.
Okay, well, thank you very much for talking to us today.
Thanks for having me on.
Thank you very much, Sam. So thank you, Sam Stranks, for joining us today. As always, if you'd like to learn more about what we've discussed in this episode and more generally about our work at the Cavendish Lab, please have a look at the show notes or go to our website www.phy.cam.ac.uk. If you have any questions you would like to ask our physicists, head to social media and tag us with the hashtag #PeopleDoingPhysics. This episode was recorded and edited by Chris Brock. Thank you for listening to People Doing Physics. We'll be back next month. Bye.